Okay, so we were talking about the difference between heat and temperature. That's fine, Angel. Just try to figure it out before Monday. If you can't, I mean, keep trying. If you can't, then we'll talk about it on Monday.
Anyone still have a problem checking in?
It's probably because the window's closed. Don't worry about it for now. Okay, we'll try this again on Monday. Okay, so if you were to heat up water, let's say 100 grams of water versus 100 grams of iron, what you would find is that it would take much more energy to heat the water than it would be to heat the iron. And that's because water and iron have different properties, a different property referred to as the specific heat. Okay, this is the amount of heat either gained or lost
Professor, I don't mind. I hope you don't mind me saying anything about your spelling, but you spelled specific wrong. Just calling it out.
There we go. You happy now?
Yes, thank you.
You're welcome. Actually, I still spelled it wrong. There you go. Now it's right. Now I have to erase the whole word because I come to new letters in there. There we go. The amount of heat gained or lost when changing the temperature of 1 gram of substance, 1 degree Celsius. And so let's say we were taking that water and the iron from room temperature all the way up to boiling, 100 degrees Celsius. So from 25 degrees Celsius to 100 degrees Celsius. Iron has a specific heat capacity, 0.473 joules per gram degree Celsius. So for every gram of iron, it requires 0.473 joules to change the temperature 1 degree. If we're going to increase the temperature, then it's going to absorb the heat. If we're going to decrease the temperature, it's going to release heat. Water, on the other hand, has a specific heat capacity of 4.184 joules per gram degree Celsius. So it takes 4 joules, almost 10 times as much energy to change the same mass of water. So to heat up 1 gram of water requires 4.184 joules, where for iron it only requires 0.473. So we can calculate the heat that something gains or loses when it goes through a temperature change. Heat is equal to mass times specific heat capacity times the temperature change. heat has the symbol Q. This is equal to M times, we use what in this class? Doesn't specify. So we use C, MC times delta T. So if we want to calculate the heat, we can ask ourselves, what is the heat required to increase the temperature of 125 grams of iron from 25 degrees Celsius to 100 degrees Celsius? And what's the heat required for the same mass of water? Go ahead and see if you can't calculate that and what you come up with. All right, so it should look something like this. Q for iron is going to be equal to the mass, 125 grams, times the specific heat, 0.473 joules per gram degree Celsius, times the temperature change of 75 degrees Celsius. Our temperature change is our final temperature, 100, minus our initial temperature, 25. So we get out of here 4,434 joules. Now we need to keep track of significant figures. So these are the fewest number of digits that we would report. And so in this case, we have 2 digits here, so we're going to keep track of our digits here. So this is going to be equal to 4.4 kilojoules, where this prefix here means 1,000. So this is 4,400 joules, or 4.4 kilojoules. From the same calculation for the water, 125 grams times 4.184 joules per gram degree Celsius times 75 degrees Celsius. We come out with 39 kilojoules. So significantly more.
So you just input all the numbers given into the calculator?
Mm-hmm.
Okay.
Other questions?
Yeah, Dr. Carlson, for the iron one, the iron calculation, would 4.4 times 10 to the negative 3 be correct, or is that wrong?
Not -3, +3. Right? So if you are moving the decimal place to the left, then the number becomes positive. If you move the decimal point to the right, then the exponent is negative. All right, so we can also use this to determine specific heat capacities of something that we don't know. Okay? So let's say the reason that we can do this is because if we take a block of metal and heat it up and place it into some water, the heat lost by the metal will equal the heat gained by the water. And this is the basis for a process, a technique that we use called calorimetry. So let's say you have a 110 gram sample of metal at 55.0 degrees Celsius is submerged into 150 grams of water, raising the temperature of the water from 23.0 degrees Celsius to 25.5 degrees Celsius. Oops. What is the specific heat of the metal? Now, one thing I want to show you here is that the heat for the water, at the heat that the water gains, is going to be equal to negative heat for the metal. And this is just so that that negative sign in front there is just so that the signs remain kind of consistent throughout the calculation. So go ahead and give this one a shot and see what you come up with. All right, how are we doing?
Yes, would we need to figure out the temperature change of the metal too?
You do. Now,
Just trying to figure
If-
that part out.
that's the point where I thought people would kind of struggle. So what happens if you drop a piece of metal that's warmer in the water What's going to eventually happen?
It's gonna cool
The
down.
water will get warm.
Water get warm, the metal will cool down, and they'll reach a point that's called thermal equilibrium. And this is where both of these things have the same temperature. So the final temperature for the water is also going to be the final temperature for the metal. So the water heats up to 25.5 degrees, the metal cools down to 25.5 degrees.
Professor, would it be 0.483513?
That's exactly right. All right. So the heat for our water is going to be 150.0 grams times 4.184 joules per gram degree Celsius times our temperature change, which is going to be 2.5 degrees Celsius. And all of that is going to be equal to negative 110.0 grams times our specific heat capacity for the metal C times our temperature change, which is going to be negative 29.5 degrees, I think.
Is that 2.5?
Where? Yeah, it says
Oh.
2.5. Yeah. Okay. So when we solve all of this, solving for C, you should get 0.4835 joules per gram degree Celsius. All right, what questions do you have?
Did you mean to put the negative before the 29.5 degrees Celsius?
Yep. Right, because the temperature change, so delta T, which is temperature change, is T final minus T initial. So our final temperature in this case was 25.5. Our initial temperature for the metal was 55.0. So this is going to give us a negative 29.5 degree temperature change, meaning that the temperature is decreased by 29.5 degrees.
Now I was just thinking, would that make the end result negative? Or that doesn't matter?
No, because we have this negative sign out in the front.
Got it.
Yeah, that's why we had to insert this negative sign. Because if I put in a hot piece of metal, it's going to cool down. The temperature change for the metal is going to be negative. We can't have a negative specific heat. Think about what that means. A negative specific heat is saying that if I put energy, heat into something, the temperature decreases. That doesn't work.
I got you.
Other questions?
Wait, so you just combine like terms and then you just plug it in how it was like from the last problem you taught us?
Well, there are no like terms. There should only be one thing that we're solving for, and that's the specific heat capacity. So literally what I calculated, C is going to be equal to 150.0 grams times 4.184 joules per gram degree Celsius times 2.5 degrees Celsius. All of that divided by negative 110.0 grams times negative 29.5 degrees Celsius. Other questions?
Yeah, Professor Carlson. So for the specific heat of, or sorry, the specific the specific heat of the substance, are we gonna be, how would we find that?
Well, just like here. Just what I told you.
I mean, the 4.184 joules over grams, how would we find that one?
That's
Sorry.
one that you might want to memorize,
Okay,
but only that one, because we use water a lot, and so knowing the specific heat capacity for water is going to make things a little bit faster for you. Otherwise, if it's any other substance, I would provide you with that specific heat capacity,
got it. Okay, thank you.
Yeah. Or that's what you're trying to solve for in that particular problem. Other questions?
So the 110 from the bottom becomes a negative.
Well, 110 times negative 29.5 would be negative, and then times this negative sign would become positive.
Oh, okay.
Yeah, I got confused. I combined the specific heat and then the weight, and I didn't count for like it's two separate variables. I think that's where I thought it was negative.
Okay.
Is 150 the mass?
Yes, 150.0 grams is the mass um, of um, of the water. Anything else? Okay. So we're going to move on. We're jumping into chapter 6 now. And chapter 6 is basically nomenclature. How do we name the substances that we are dealing with? We already know that elements have particular names, but how do we name the molecules and compounds that we're looking at? So there is a systematic naming system that we are going to follow. Now, elements, we can name an element fairly easy. In terms of ions, we have a couple of different ways. And so we're going to start off talking about ionic compounds. Okay. So remember, this is something that has either a metal or ammonium and then some non-metal or a combination of non-metals. So to begin with, the first thing that we're going to do is when we get the name of a formula, is we're going to name the cation. So let's take a look at, let's see, let's look at, which one do we pick? Let's pick fool's gold. So we're going to talk about this compound. So the cation is the species that is written first. In this case, it's just iron. Okay. So what happens is that iron let's pick a different one. Iron to bad example because iron's doing something weird. We'll just do an easy one. We'll do sodium chloride. All right. So we named the cation. What we have here is we have a sodium going to sodium and an electron. For the most part, generally, our metals are losing electrons. Now, again, that's not always true, but for our purposes right now, a metal is going to lose an electron. Okay. The way that we name the cation in this case is just the name of the element. Now, this actually only happens if the cation only forms one particular charge. We'll take a look at instances where the cations might have multiple charges, but for right now, it has just one particular charge. So we just named the element. So in this case, it is sodium. So this here is the sodium ion. We don't say the word ion, we name the compound. So it's just sodium. Then we name the anion. And in this instance, it's a chlorine atom gaining an electron to form this anion. Okay. So here we take the root of the elemental name. And you change the ending to IDE. So the root of this here is going to be chlor. So this becomes the chloride ion. Now, when we name the compound, we drop the words ion. And so what we would have would be sodium chloride. All right. Give this a shot. How would you name this compound?
Is it aluminum trioxide?
Why would you say trioxide?
Because of the 3 in front of the oxygen?
So not quite. Remember, we don't need to specify this. We don't need to say that there are 3 oxygens that are present. So this is just aluminum oxide. So that's it. We don't need to specify that there are 3 aluminums. It's just aluminum oxide. The reason we don't have to specify this is based on the fact that elements tend to form certain charges. So 1A metals, lithium, sodium, potassium, rubidium, cesium, they form +1 ions. 2A metals, beryllium, magnesium, calcium, strontium, barium form +2 ions. Aluminum is always a +3 ion. On the anion side, 7A, they form -1 ions. So these are the halogens: fluorine, chlorine, bromine, iodine. 6A, so oxygen and sulfur. So O2- and S2-, they form -2 ions. Generally, again, these aren't hard and fast rules. It's not always going to be this way, but for the most part, it tends to be that way. And then 5A, right, we get nitrogen -3 and phosphorus -3. They tend to form -3 ions. There are some other rules. For example, zinc always forms +2. Cadmium always forms +2, silver always forms +1. Those are things that we can talk about and address a little bit later. But for right now, we have these kind of rules. So recognizing here, aluminum forms a +2 and oxygen a minus, sorry, aluminum forms a +3 and oxygen forms a -2. We know then that we don't need to worry about saying trioxide because we know how many oxides there are, because compounds are always electrically neutral. Meaning that the total positive charge has to equal the total negative charge. And this is where things can get interesting, because we have something like this. The transition metals typically form more than one charge. Iron typically forms more than one charge, forms a +2 and a +3. So I can't just generically say iron oxide. So, because if I say iron oxide, which one am I referring to? Am I referring to FeO or am I referring to Fe2O3? So what we do is, for a metal that can form more than one cation, right? So Fe2 plus or Fe3 plus, you specify the charge in the name. So for example, this is iron 2 oxide. And this is iron 3 oxide. So we specify the charge using Roman numerals in the name. Now, how do I know that the first one is iron 2? I know the first one is iron 2 because oxygen has a -2 charge. In order for this to be electrically neutral, that must mean that iron has to have a +2 charge. That's pretty straightforward because there's only one of each. However, in this case, with iron 3 oxide, again, my oxygen forms a -2 charge. However, there are 3 of them. So 3 times -2 is equal to -6. That must mean that iron is equal to +6. There are 2 irons. So +6 is equal to X times 2. X therefore must be +3. So that's how we are able to come up with the charge for iron in there. So you can either determine the charge based on the charge of a cation, based on the charge and number of anions, or if you're given the name, you have it right there in the name. So
Sorry, Professor.
Mhm.
So how do we know a metal can form more than one cation?
if it's a transition metal,
Okay.
there are just 3 transition metals that don't: silver, cadmium, and zinc. Silver always forms a +1. Cadmium and zinc always form +2 ions. All of the rest of the transition metals can form more than 1. Some of them can form more than 4.
What was cadmium again?
Cadmium is a +2. So how would you name then? Oops, how would you name this?
Is it copper 2 chloride?
Yeah, copper 2 chloride. Remember, so chlorine is a -1. There are 2 of them. So this whole portion is -2. That means copper must be +2. It's exactly right. This is copper 2 chloride. Spectacular. What about that?
Chromium, nitrogen, but chromium being 3.
So
Is it chromium 2
2.
nitrogen?
So you're right. It's chromium 2, but it's not nitrogen. Remember, we have to change the name of the anion. So yeah, so I got it right. Chromium 2 nitride.
So we can just like kind of swap it, or like do we have to do all the math?
Oh, okay. I see what you're saying. So you can't, you kind of have to do the math, but sometimes you can swap it, right? So if we talk about the aluminum oxide again, right? If I'm going to say, what is the compound formed from the aluminum ion and the oxide ion, oops, like this, right? You can go generally, okay, well, this goes here and that goes there. And so we're going to get out of this Al2O3. That tends to work. You do need to keep in mind that you do need to take it down to the smallest whole number ratio. What do I mean by that? Well, what happens if you have manganese 4 and oxygen like this? Well, if you follow that rule, what you're going to have here, again, that goes here and this goes there, what you would have is Mn2O4. We actually have to take that down to MnO2. And now this only pertains to ionic compounds. When we talk about molecular compounds, those do not need to be in the smallest whole number ratio. Ionic compounds, the subscripts must be in the smallest whole number ratio. All right. we're gonna stop there for today. In your textbook, practice. For the example problems, there are some practice ones underneath it. Practice number 6.3, 6.4, and 6.5. And we're going to start off next Wednesday. Remember, we don't have class on Monday. It's a holiday. So we're going to start off next Wednesday talking about how to name binary compounds that have two nonmetals present, as well as how to name compounds that have polyatomic ions.